Hi everybody, this is Mr. Couple. Welcome to our second online lesson. Today we'll be learning three things. We're going to be learning about Coulomb's law, conductors, and charging. So this is kind of going off where we left off last time. There are three main ideas for the lesson today. So our three main ideas today are that Coulomb's law describes the strength of the force between two charges. You'll remember this as the inverse square law. We learned about this with gravity. And also, the second main idea is that materials that allow charges to easily move around, those are called conductors. And the opposite is where charges aren't free to move through these materials. Those are called insulators. And then the last idea today is that objects can be charged through friction or through something called induction. So altogether, when you talk about how can we describe the force that charges exert on each other, we'll be talking about how charges can move through objects, whether they are conductors or insulators. And then lastly, we'll be talking about how do you make objects become charged in the first place. The first thing we're going to talk about is comparing gravity and electricity. So gravity is something that we're all very familiar with. Like you've experienced it your whole life. It's this force pulling you down, sticking you on this planet. But we haven't really thought too much about electricity. I mean, we did some experiments in class with the tape. We pulled the tape apart. You probably have also scuffed your feet against the ground and built up a charge and shocked yourself on a door, things like that. But what we want to really understand today is what is it about gravity and electricity that's kind of the same, and what is it that's the opposite? And so we sort of started this last class. I just wanted to continue with this today. So the first thing we want to talk about is where do these forces come from? So what is the source of gravity? What do you need to have in order to feel or create gravity? What do you need? Someone can jump in and say it. You need mass. So gravity, I can't even read that. Maybe I can try green. So you need mass in order to feel gravity. What do you need to feel the electric force? What property do you need to feel electricity? You need charge. All right, so what we can see here is that we have planets going around the sun. Well, the sun has mass. I'll call that big M. Okay, I just forgot pink doesn't work on there. So the sun has a big mass, and then the planets have a little mass. So there's the Earth. And so what's going to happen is the mass of the sun is going to exert a gravitational force on the Earth, and that's going to be the force that keeps the Earth in its orbit. We call that the gravitational force. Very similarly to that, you have an atom on the right-hand side, and the atom has a charge. And the atom, the nucleus of the atom, has a positive charge, and Q is the symbol that we use for charge. It's kind of confusing because we also use heat as Q, but we use Q for charge. Capital Q and lowercase q are interchangeably used for charge. So the nucleus is positively charged because it has all those protons in there. Usually the red ones are the protons. So you've got all these protons in there that all have a positive charge. The neutrons, they don't have any charge. So it's just these positively charged protons in there. Then whirling around the nucleus, we have, what are out here? These guys. What are they? Those are the electrons. The electrons have a different type of charge than the protons do. They have a negative charge. So what happens is if you have a positively charged place and a negatively charged object, what's the positive place going to do to that negative charge? It's going to attract it. And so you're going to have a force pulling the electrons. What letter was that? You're going to have a force pulling the electrons towards the nucleus. So the electrons will actually orbit around in this model. This is called the planetary model of the atom. The electrons will actually orbit around the nucleus where the centripetal force to cause it to move in those circular orbits is provided by the electric force. So these two forces are very, very similar to each other. And we'll be talking even more about this because you can also describe fields created by these forces or how the forces are transmitted through fields. Like we talked about the gravitational field where that was G. We can also talk about the electric field. And we'll be talking about that next week. All right, so here's that picture again, that a satellite going around the planet is very similar to an electron going around a proton. Obviously, they're at completely different size scales, where the planet is a really huge scale, and then the little tiny atom is a tiny, tiny, tiny thing. But both laws of physics apply whether you're talking about the tiny scale or the large scale. All right, so you guys might remember this. We talked about the force. We actually derived this in class, the force between these two objects. We call this m1, we call this m2, and then we call the distance between them, we call that r. And there's an equation that we can write that relates all of these quantities together. Do you guys remember what that is? It's F equals, this has been a long time since we did this. So do you remember the equation for gravity? Nope, that's the gravitational field equation. When we're talking about two objects pulling each other, we have to use the more general version of it. I can give you some hints. It's m1, m2, that's it. So the force is this constant g, which was called Newton's universal gravitational constant, times the two masses, m1, the mass of the planet, the mass of the satellite, divided by the distance between them squared. For electricity, it looks exactly the same, just we use different letters. So this is called Coulomb. Coulomb, it's a French name. It's called Coulomb's law. So instead of M, we have charge, we have Q. So you're gonna have Q1, Q2, and then there's gonna be that force acting. And it's also gonna be because they're separated by a distance, which we call R. So the equation is gonna look very similar. It's gonna be F equals, we're going to have this K, Q1, Q2 over R squared. That looks like a V. Let me try that again. Over R squared. So what happens is it looks structurally the same. You've got this inverse square for both of them. Inverse because it's on the bottom. We have inverse square for universal gravitation and inverse square for Coulomb's law. The difference, though, is with this constant out in front. They're going to have these different constants. So for universal gravitation, the constant g is 6.67 times 10 to the negative 11. And the units of that are newtons, meters squared per kilogram squared. Run out of space. Let me move that over. And then for the Coulomb's law, the K value, so K, I'll do it in pink. Whoa, what happened over there? What was that? That was a G? Okay. For Coulomb's law, K ends up being 8.99 times 10 to the 11th, I'm doing this wrong, 9th power Newton. Now it's not, it's still meters squared, but instead of kilograms, it's the unit of charge, which I'm not going to ever tell you guys because we don't need to know it. But the unit of charge is called the Coulomb. Now, just at face value, like what do you notice about these two constants? So what do you notice about the two constants in this equation? Like if you were to compare their sizes. Gravity is tremendously smaller for that proportionality coefficient. So you have, if you looked at the difference between those two, it's billions of times different. And so what we usually say is because of that G being so small, like think about this, gravity is an incredibly weak force. Like if you guys like take your hand and lift it up, like lift up your hand, you just defeated an entire planet's worth of mass trying to pull your hand down. Gravity is incredibly weak for that reason because this G is so tiny. But electricity, the constant for electricity is really big. It's way stronger. And so smaller objects can really exert strong electric forces, whereas small objects are irrelevant with gravity. And so you guys remember like the balloon, when you rub the balloon on your hair, and then we picked up those little pieces of paper when we did that in class. We said that the electric force in those little tiny objects like the balloon and the paper, that electric force was really strong, that it was able to defeat the whole planet pulling those papers. That the paper was able to stick to the balloon even though the whole entire Earth was pulling it down. So the idea is that because this number is so big, the electric force is noticeable even when you have small amounts of charge. Whereas the gravitational force is only noticeable when you have a ridiculously large amount of mass. What questions do you guys have about this? It stands for Coulomb's constant. It's just K for constant. We call that in mathematics, you call K a proportionality coefficient, or like proportionality constant. Okay, there's this PhET simulation that I'm going to have you guys go play with if you want to, as one of the options, the choice. It's part of like the choice wall for this assignment. I'll show it to you guys real quick. So what we can do is we can like move these charges around to different places from each other. It'll tell us how much force there is. We can make one charge bigger. We can switch them to being both positive, then they repel. We can switch them to being positive and negative, then they attract. So you can play around with this, like you can change the amount of charge and things like that. But what I'm going to do is just pull off right here. So Coulomb's law is K Q1 Q2 over R squared, and then that K is 8.99 times 10 to the 9. So what's the given information in this setup? We're going to try to figure out the force between these objects. So what's Q1? So if we look at our diagram over here, here's charge 1. So Q1 is equal to, and we got to look, so it says 4 microcoulombs. So Coulomb is the unit of charge. So I'm going to write that as -4, and now I have to write down micro. See if you guys remember your metric multipliers. It's -6. And then Q2, we'll do it in pink. Q2 is 8 times 10 to the same thing. It's micro, -6 coulombs. And then the last question I have is, well, what's the distance between them? So what's the distance between these two charges? So it's I don't is it 2 though? I mean, where are we measuring from? Are we measuring from here to here? We're measuring from the center to the center. So just like with gravity, you always measure objects to their center of the object. So that is indeed from 4 to 6 is 2 centimeters. So we have to express this correctly. So it's 2 times 10, and then centimeter is negative. Does anyone know? It's -2. Right, so you can think of like a cent. Like there's 10 to the 2 cents in a dollar. So 1 cent is 10 to the -$2. That's centimeters. All right, so here's my first question. So which of these two charges, Q1 or Q2, which charge is going to be acted on by a greater force? We're going to draw arrows to show the relative strength of the force in each charge. So here you've got a big honking 8 versus a little tiny 4. So which charge is going to be acted on by a greater force? I'm going to let you guys think about that for a minute. You can jump in the voice chat and share your thoughts out loud if you want to, but we're going to ask which charge is acted on by a greater force. Embarrassed to say anything. Well, how about this? What are they going to do? Are they going to attract or repel each other? Right, so they're going to attract. How do you know that? Exactly, they're opposite charges. So my question is, which one's going to be pulled more? So we know that the blue charge is going to pull the red charge to the left. And then we also know that the red charge is going to pull the blue charge to the right. My question is, which one's going to get pulled more? Is it the blue one? Yeah, I was just repeating your question. Is it the blue one? So why would you say the blue one, Ben? Okay, so the one with less charge is going to get pulled by a stronger force. Is that what you're saying, Ben? Okay, anyone else have any thoughts on this before I tell you the answer? Which charge is going to be pulled by a greater force? Nope, it looks like we've all forgotten Newton's third law. If one object exerts a force on a second object, the second object exerts a force on the first object of equal magnitude. In the what direction? opposite direction. So they have to have the same force. So it doesn't matter whether they're the same charge or different charges, they're always going to exert the same force on each other. And we can see that in the equation up here. You have two charges, but only one force between them. One force magnitude. There are two forces, one on Q1, one on Q2, but the two charges exert a single force in one magnitude force. They're just going to be in different directions on each object. So we can calculate the force. So let me zoom out. Okay, so to calculate the force, we just have to use Coulomb's law. So it's K, Q1, Q2 over R squared. So we know what K is. It's given as 8.99. Let's just call that 9. 9 times 10 to the 9. And then we'll multiply that by Q1, which was negative 4 times 10 to the negative 6. And we'll multiply that by 2. Did I do this right? 8. Q2 is 8 times 10 to the negative 6. And then we're going to divide that by R, which was 2 times 10 to the negative 2. And then if we throw all those numbers in a calculator, we'll have the force between them. So where did my calculator go? It's somewhere. I remember where I had, I thought I already had it out before I started recording. That's funny. There it is. Okay, so I'm going to take, so here's how you put this in a calculator. Type 9, and then I'm going to go EE, 9. So I just wrote 9 times 10 to the 9. The little e stands for times 10 to the. I'm going to multiply this by negative 4, second EE to the negative 6. I just wrote negative 4 times 10 to the negative 6, times 8 times 10 to the negative 6. I forgot to put a multiplication over here. I'll get confused if I don't do that. Okay, and now I've got 9 times 10 to the 9 times 4 times 10 to the negative 6 times 8 times 10 to the negative 6, and then I have to divide that by 2 times 10 to the negative 2, and then I just have to make sure that that bottom number is in the equation. You can see the bottom number is squared. So I just have to remember to square the bottom, which is what you just saw I just did it. We always forget to do that. So I have to raise that to the second power, so there's my squared button there. And then I get the answer, negative 720. And then what are the units going to be on this? So this is Newton meter squared per Coulomb squared. This is Coulombs, and this is meters squared. So what will happen is this Coulomb and that Coulomb will cancel the Coulomb squared. This meter squared will cancel that meter squared, and we're left with newtons, which is a force. So that's an example of a calculation that you do with Coulomb's law. But basically this equation is used to calculate the force that charges exert on each other. What was that? All right, so now I want to talk about conductors and insulators. So you guys have probably all plugged a device in. I mean, I'm using one right now. So these wires, they're made of copper. So copper, if you were to look at the atomic structure of copper, so remember we're talking about like atoms and how they have like electrons whirling around them. This is going to be really important to understanding electricity. So this is what copper looks like. Copper has a lot of electrons. Remember, atoms always have to have the same. My computer is lagging a bit. I think that I need to close the calculator. Okay. If you remember last time we said that atoms always have the same number of protons as they have electrons. My video is super laggy right now. I don't know what's going on. So copper, inside of it, has a lot of protons. I don't remember the exact number, but you can see all about here, there's tons and tons of electrons. Now, the way like the electrons orbit around the atom is really complicated. You'll learn about that in chemistry next year. But all that we care about right now is the fact that there's this one electron way out there, far out, and we call that a free electron. And so the thing is that the distance that this electron is from the nucleus, which is what's attracting it, which is what's pulling it in, it's really far away. And so when the distance gets further away, what happens to the force that's acting on it? It's going to get way smaller. So that electron is very loosely held on by the nucleus. That electron, in fact, is so loosely held on that it will actually drift away and maybe join up with other atoms. So all these different blue dots here, these are the electrons like moving around, and then the red dots are the nucleus. So we say that all these other electrons on here, like the other ones that are inside, like they're all stuck in there. Like they're not going anywhere. They're close enough in that they're being pulled. But that free electron is so far out that the force is like kind of weak on it. And so it's actually able to sort of drift around and move between atoms. So here's an animation of that. So you can see like these free electrons, they're so loosely held on to their atoms that they just kind of move around and they'll bump into or transfer between atoms. So this is what happens inside copper. There's also this, which is if you make a wire of this stuff, like if you put a bunch of atoms in a row and you make a wire, you can see that the electrons can actually flow from one atom to the next atom. And we call this a current or a current flow. Okay, so here's my question. What happens if a conducting material such as copper, these are called conductors, is placed across the terminals of a battery? So here we have a battery, and you can see all those different electrons in there. What happens when I connect them to a battery? What are those electrons going to do? Do you guys know what they're going to do? These free electrons that are just hanging out and around, moving around. What's going to happen when we connect it to a battery? Any guesses? It's going to generate electricity. This is what will happen. The charges will start to move through the wire. And so what you're seeing there, those little blue dots, those are the charges that are freely traveling from one atom to the next. They're just traveling through the wire. This is what we call electricity. All right, so in order to do that, you have to be what's called a conductor. The material has to be a conductor. It has to be able to allow charge to flow through it. So looking at these pictures here, which of these would also allow charge to flow? So here you have a paper clip, we have a dollar bill, we have a coin, a metal coin, and we have an eraser. So I want you guys to just think to yourselves, which of these will allow charge to flow and which of these will not allow charge to flow? The coin is a metal coin. So like it's made of aluminum or nickel or copper or zinc, whatever you want. It's some metallic coin. A metallic, whatever metal you want. Yeah, any metallic. I'm not trying to trick you guys here. I just noticed that I accidentally left the charges on display here. I didn't mean to do that. Sorry about that. All right, I want someone to say one where they think the charge will flow. Say it out loud. Which one do you think charge will flow through? Okay, let's check it out. Yep, charge can flow through a coin. So what does that tell you about the material that the coin is made of? It's conductive, which means it has a lot of free electrons and those charges can flow through it. Okay, I also heard someone shout out paperclip. Let's check if that one's right. Yep, the paperclip is also a conductor. Generally, we say that things that are made of metal, like gold or nickel or steel or iron, like those are all going to be conductors. Okay, what do you guys think about the dollar bill? Do you think it's going to let charge flow through it? It doesn't. Paper is not a conductor. So paper, in the atoms that are inside paper, the electrons are really tightly packed in there and they're not able to move around freely. What about an eraser? Nope. Yeah, eraser is not. What the heck? What? Oh my gosh, all of my animations are still loaded down here. Okay, yep, so there it is. The eraser is not a conductor. Charge cannot flow freely through an eraser. To indicate how well charge can flow through material, we use two terms. We use the word conductor when it can flow, and insulator when it can't flow freely. In a conductor, the electrons are loosely held and they're free to move. So you can see here in the conductor, the electrons are loosely all over the place and they're just like they're flying all over the place, moving all over. That's a conductor. So some examples of that are copper, gold, seawater, fresh water is not a conductor. You have to have salt in it or impurities to be a conductor. And an insulator is where the electrons are trapped. So you'll notice over here in the insulator, there aren't really any free electrons. Like there's one right there, but there's really not many others. And that's because all the electrons are trapped and they're stuck on the atoms. They're not really able to move around. So some examples of insulators are paper, rubber, wood, cotton. So those are things that you wouldn't expect electricity to flow through. So basically conductors allow electricity to flow and then insulators resist electricity to flow. So here's the question. Why do we make electrical transmission lines out of metal? You got it. So that electricity can flow through them. So we need, if we're going to send electricity across many, many, many miles of distance, you're going to need a material that really allows that charge to flow through it easily. So you would not make wires out of wood. That would not work. You need it to be made out of metal so that the charge can flow freely through it. You may have also heard of these materials. They're called semiconductors, and the other ones are called superconductors. So semiconductors are kind of like in the middle. Like they're not good conductors, but they're not good insulators. And they can actually be made to switch between conducting and insulating. Like they're just like borderline between being able to conduct and to not conduct. So they're called semiconductors. And you can see here like the structure, it's usually silicon is the atom that they're made of. Like computer chips and stuff like that are made out of silicon. And so if you look at the atomic structure, you'll notice that it's all filled up. Like there aren't any free electrons. But if you like manipulate the material, you can actually kind of like poke holes in it and like pull some electrons out, or you can give it extra electrons. So it's kind of like on the borderline where it's like, it's just full enough, but it's not like, it can sort of trade, like switch teams easily. And so because of that, you can send electrical currents at will through them. Like you can turn it off or you can turn it on like really easily. Like that's called the binary, like zeros and ones and stuff like that. You guys have probably heard about computers and how they create code like through zeros and ones, like on and off. So silicon is able to do that. It's called a semiconductor. And another thing that you may have heard about are called superconductors. What superconductors do is they actually, they have no resistance at all to charges flowing through them, that they actually like propel the charges through. And so if you send a current through a superconductor, it will never stop flowing. And you can use this to create magnetically levitating trains, and you can use this to create particle colliders where they like smash particles together at like 99.99999% the speed of light. Briefly, the way a superconductor works is that the material is so loosely held together, like these bonds are so loose that actually the electron will pull these protons towards it. And now you've got this clump of positive charge here from all these atoms being pulled in by that electron, that it actually creates a dense clump of positive charge that can then pull and accelerate other electrons towards it. And so you actually end up getting this like self-feedback where it's like pulling the charges through it. And so we call it a superconductor, and it's usually only possible at very low temperatures where the bonds, like where these atoms aren't moving around very much, that they can actually kind of be pulled and moved by the electron. Normally at high temperatures, these things are oscillating around so much, they're just like, that the electrons have a really hard time pushing through there. Okay, I'm going to pause for a minute, see if you guys have any other questions. I'm almost done. Gold, of course. Because gold's really rare, and it's, you know, forged inside the collisions of neutron stars. Like, that's amazing to me. So later on, we'll learn about how electricity can create magnetic fields. So if you have a normal wire where there's resistance in it, if you try to send a current through it, it'll heat up like really, really hot, and you'll lose a lot of energy. But if you have a superconducting wire, you can send a current through it, and it will never stop flowing. And so that way you can continuously make a strong magnetic field that can lift the train. You would not be able to do that without superconductors. It's a requirement that you don't lose any heat or energy to the resistance of trying to push electrons through a material. I have no idea. That's beyond my knowledge. Generally speaking, materials are not superconductors unless they're very cold. And I believe you could probably turn most materials into a superconductor if you cool them down to a low enough temperature. Like down towards absolute zero. They are materials, but I don't off the top of my head, I don't know any of them. Yeah, if you take a material and you cool it down really, really cold, a lot of materials can turn into superconductors. I just don't want to say the wrong answer. I don't know, but you can make them out of almost any material you want to. There's every material is gonna have a different cutoff where it becomes a superconductor, a temperature cutoff. Out of your arm, I don't know. Maybe if it gets cold enough. Let's see. The last thing I was going to show you guys was just how do you charge an object. So you can charge an object by friction, by like rubbing two objects together. So this kid was sliding down the slide and he became charged because as he slid down, electrons were transferred between the two materials, from the slide to the buoy or from the buoy to the slide. I'm not really sure which way they went, but the electrons are transferred. And as a result, two what used to be neutrally charged objects have now become charged, where one has gained electrons, become negatively charged, and the other one has lost electrons and become positively charged. You can also charge something by contact. So here is one of my students, that's Sui. She's a senior now. This is when she was in 9th grade. But she's touching this positively charged object. And so what's happening is it's sucking all of the negative charges in her body are being attracted towards it, and all of the positive charges in her body are being repelled from it. And so she becomes positively charged as this positive object is pulling all her negative charges away. Then I was supposed to show you guys this video. I don't think I have time for this video, so I'll probably just post it up for you guys to watch it on your own. But there's another way that you can charge objects, is if you bring an object that's charged. So if you bring an object towards another object, it'll end up pushing all the negative charge. Now they're not actually touching. You'll notice that this rod, there's a gap here. They're not actually touching. In the case of Sui, she was actually touching. So here we have, this is called induction. So induction is where you make something charged without actually touching it. So what will happen is, because there's such a amount of positive charge here, it'll end up pushing all the negative charges over to this sphere. Should probably use a different color there. It'll end up pushing the negative charges over here. I did that backwards. It'll end up pushing the positive charges over here because they'll be repelled from this positive, and then the negative charges will get attracted over here. And then if you bring the spheres apart from each other, so if you separate them from each other, you'll notice that this one will have a positive charge, so it will repel this positively charged tape. And this one will have a negative charge, and it will attract the positively charged tape. So this is a way that you can charge objects without rubbing them or without actually touching them. You can charge by bringing an object that is itself charged near to it, and it will cause the objects to become charged. So this is called charging by induction. It's where charge is transferred without physical contact. This is what happens in a lightning storm. You have this buildup of negative charge at the bottom of the cloud, and what that does is it ends up pulling positive charges up from the ground. And so now you have this extreme separation of charge between the ground and the cloud. And then what will happen is it'll actually rip electrons off the air, like it'll ionize the air, it'll build its own wire, it'll like forge its own wire through the air to create a lightning strike. And so that's working off of this principle of induction, where you charge without touching. Yeah, what's up? Yes, that's definitely true. So the way to explain that is, what happens, it's really complicated. I wish I should have shown you guys this video, but the storm, when you have this buildup of charge, it actually sends out feelers like in every direction. So like it's looking for a place to dump the charge. It doesn't like having this huge buildup of negative charge. So there's like these little feelers that kind of come out. They look like branches of a tree. And as soon as one of those hits something, then you're going to have this lightning strike's going to occur. So it's more likely that you're going to find one of those feelers is going to find the ground to a high building before it would find it to like underneath, like by a tree or something like that. About this one? Yes, that's correct. The next lesson is going to be about fields. But yeah, that's exactly what's going on, is that we have these electric fields that are radiating outward. So this object that we brought near to it, this is actually creating a field around it. And so that field is exerting forces on charges that are in the field. And so it's pushing the positive charges away and pulling the negative charges towards it through this electric field. I have no idea what the answer to that question is. I don't think anyone knows. We just say that this influence that charges exert outward is called an electric field. We don't know what it's made of. We have no idea what it is. It's just, we call it a field. It's just our way of explaining how objects know to feel a force. It's the same thing like with a gravitational field. What is the makeup of a gravitational field? I don't know. Is it even real? I mean, we see the effects of it, but is it a real thing? That's a philosophical question. I think I went over. I'm sorry, guys. I think I went like 5 minutes over. But I am finished, so I'm going to stop the recording here. If you guys want to hang around and voice chat afterwards, that'd be awesome. But have a great day. We're done.